Hi, my name is Tiagi, and in this video, I'll be going over Unit 5 of AP Calculus A, B, and BC, Analytical Applications of Differentiation. So to start, before I start going over this unit, the key thing I want you guys to take away from this unit is that differentiation is immensely powerful and useful for helping us to not only find derivatives, but it's immensely powerful for helping us find key attributes of a function, such as the maximum, minimum, and help us with optimization. So with that being said, let's start with the first theorem you need to know for this unit, which is the mean value theorem. So the mean value theorem states that for a function f of x, if it's continuous on an interval ab, closed interval ab, and differentiable on an open interval ab, then the mean value theorem states that there has to exist some c such that f prime of c is equal to fb minus fa over b minus a. So in normal words, what it's saying is that there has to be some instantaneous rate of change that equals the average rate of change from b to a, which makes sense because it's continuous and differentiable on that interval. So for example, let's say we have point A here, point B here, and it's continuous and differentiable like so, and that's the function. What this is telling us, the mean value theorem, it tells us that because we have it's continuous and differentiable, there has to exist some c, like here maybe, such that the slope from b to a, like this, there has to exist some c such that the derivative f prime of c is equal to that. And clearly, from the visual, we can tell this works for any function, right? Because here we have a and b, that's continuous and differentiable, therefore f prime of c has to be somewhere on this line such that it equals the average rate of change. This also brings us into Rolle's theorem, which is a kind of application or a smaller subsection of mean value theorem. And basically the idea is that if we have FA equals FB, right, and we have F prime of C, F prime of C equals 0 somewhere along this place, which makes sense, right, because FA, FB, that means that our average rate of change is equal to 0, therefore F prime of C should equal 0. For visual, if we have A and B, right, they have the same height, so if we imagine the line connecting them, that means there has to exist some value, f prime of c, such that the derivative is equal to 0, which you can clearly see is right there. Next, let's go into extreme value theorem. So the extreme value theorem is pretty basic, but it states that if we have f continuous on the absolute value, or sorry, closed interval ab, then there has to exist a minimum and a maximum value on the interval, which makes sense, right? If we have a continuous function, right, there's going to be a minimum value and there's going to be a maximum value, and this can be the endpoints right here. That would be the minimum, that would be the maximum. So the important thing to realize is for all of these theorems I listed, you have to have a sentence justification to get credit on the AP exam. So in the description below, I actually have a sheet with my notes on it, and I have a sheet with all of the sentences you need to earn credit for this unit, FRQs. And I'm not going to go over the sentences in this video just for the sake of time, but if you want to follow along with the theorems, the description has all the sentences you need in order to get credit. But the main idea is whenever you make a sentence, you always want to say something about the continuity or differentiability if necessary, and then just say something about whatever the theorem says. But again, the whole sentences that you need will be in the description below. Okay, so the idea of min and max is actually really important, and there's two types of minimums and maximums. There's absolute minimums and maximums, also known as global, and these are the maxes slash minimums on the entire domain of a function. And then there's relative or local maxes slash minimums, which are the max slash minimum on an open interval. So not the entire domain, but on an open interval I. So let's imagine now, just to really understand this, because this is important that you understand the difference between absolute and relative. Let's imagine we have a function that looks something like this, okay? And this is the interval from here to here, that's the domain. Okay, so first, let's identify all the points as maxes, relative, or absolute. This one is an absolute minimum, right, because it's the lowest the function reaches on the entire domain. This is the maximum, right, because it's the highest it reaches on the entire domain, and it is a relative maximum as well. And the reason why this is a relative maximum, but not this, is the open domain, right? So imagine, sorry, we have a open interval, right, from here to here. The maximum on that open interval would be that point. But this cannot be said for this, right? For this point, if we make an open interval from here, the endpoint, to here, there is no minimum because the open interval does not include this point. The open interval does not include that. Therefore, there is no relative minimum on that interval. While here, we can make an open interval such that's a maximum. So that's why that's a relative maximum, and that's not a relative minimum. Okay? Here we have a relative minimum, because again, open interval, relative maximum, again, open interval, and that's all the extrema, which is what we call them. Maximums and minimums are called extrema of this function here. And a main important idea to realize is that critical numbers, which are numbers such that f prime of x is equal to 0, so f prime of c, right, at c. So critical number is that x equals c, f prime of c equals 0, or f prime of c is equal to undefined. Right, so critical number is important in telling us that the function is behaving weirdly at a certain point. And the idea is, with critical numbers, they're important, for us at least, because they can tell us the relative extrema. So relative extrema, wow, my spelling, only occur at critical numbers, right? So in these cases, right, if you imagine a maximum here, at this point here, the derivative equals 0, and therefore it's a critical number, right, because the derivative equals 0. And if we consider, for example, an absolute value function, it's no derivative here, right? At that point, there's no derivative at that maximum. F prime of c is equal to undefined. So the idea is, if you ever have a critical number, f prime of c equals 0, undefined, or sorry, if you have a relative extrema, like so, then you have to have either f prime of c equals 0 or f prime of c equal undefined. But an important thing to realize is that just because it's a critical number, right, just because it equals this or this, does not mean it's a relative extrema. And the counterpoint would be, if we imagine this function, right, negative 1 over x, this is a critical number right here, right, at 0, but that isn't a minimum or maximum, right, because there's no open interval you can make such that it's a minimum or maximum. So the inverse isn't true, right? Relative extrema means it's a critical number, but a critical number does not entirely mean it's a relative extrema, right? Because this example shows that just because it's a critical number does not mean it's a relative extrema. Okay, next we'll go into identifying when a function is increasing and decreasing. This one should be pretty obvious, right? You should probably know this one, but the idea is, if we have a function, the derivatives tells us the slope. And so if f prime of c is greater than 0 on an interval, it's increasing. If f prime of c is less than 0 on an interval, it's decreasing. And of course, if it equals 0, it's neither. And if it's undefined, then there is no, and something weird is happening there, right? It could either be a infinite discontinuity or some kind of discontinuity is happening there. Okay? And the idea is, an important thing we want to know how to do is identify intervals of increasing and decreasing. And the way we do that is we first identify critical numbers, right? Because the critical numbers are where the function changes either to increasing or decreasing. And then we draw a number line. We're going to label the number line as f prime of x, and then we're going to write it in our critical numbers, critical number 1, critical number 2, and then we're going to test out points and see if it's positive or negative. So here we test out a point, so pick like any point before c1, plug it into your f prime of x function, or sorry, f prime of x, and see if it's positive or negative. So let's say it's positive, right? That means the function is increasing, so it's increasing here. Negative, that means the function is decreasing here. Positive again, for example, that means the function is increasing here. So a graph would look something like this, right? So we have positive, it's C1, then negative, right, it's going down. Then we have C2, positive, and then it's positive after that. So positive, negative, positive, which is what our number line shows, and we figure this out by finding out the critical numbers and then testing out for the intervals in between. Okay, so this leads to our first test for finding extrema, which is the closed interval test. So the closed interval test is used when we have a closed interval and we want to find the absolute extrema. So we want to find the actual absolute extrema and we have a closed interval. And the idea is we want to find the critical numbers. So we want to find when f prime is equal to either 0 or undefined. And then once we find that, we're going to create a table, x, f of x, and we're going to say on the left side, again, we have an interval, right? So a to b. We're going to start with a, right? Start with a, and then we're going to go all the way using all our critical numbers. So critical number 1, critical number 2, all the way to however many critical numbers we have, all the way to b. So we're creating a table with x values with a and b, so our sections of our interval, right, the starting and ending points, and all the critical numbers, and we're going to find what f of x is on all these intervals. Then, once we find f of x, we're going to say, okay, what is the max f of x, right? That means x equals a is a maximum. And then what is our min? That means that x equals a is a minimum. And of course, there's a sentence for this as well. One thing to realize though with closed interval tests is you got to be careful about whether it's asking you for the point at which it's a max or minimum, or the point at the value at which the value of a maximum or minimum, right? Because the point would be x equals blah blah, but the value would be the actual y value at the maximum or minimum. So be careful on those types of questions and the wording on that. Okay? Next, we'll go over the first derivative test. And again, there's sentences on all of these which you need to know, and they are in the description below. So first derivative test, the idea is, again, we're going to take the critical numbers again, and we're going to create a number line. So find critical numbers, and then create a number line like we did before. So it looks something like this, right? We have number line labeled f prime of x, critical number, and then we label increasing, decreasing areas, so positive, negative, positive. And the idea was with the first derivative test, there's a maximum at the critical number if f prime of x is positive before and then negative after. And visually this makes sense, right? If we have f prime or f of x, here it's positive, here it's negative, and there's a maximum, which makes sense because the function is going to be doing something like this. Positive and then negative, which makes sense, which is why it's maximum. Vice versa, if we have f prime of x is negative, then f prime of x is positive, which would look something like this, right? We have a negative and a positive, right? Then it's a minimum. And again, this only happens to critical numbers, so f prime of c has to equal 0, or f prime of c has to equal undefined, like so. Okay, and that's the first derivative test. Next, let's talk about concavity. So concavity tells us how the derivative is changing. So the concave up means that the derivative is increasing. And the two situations we have are like this or like this. And so you can see here, derivative is here, then the next derivative is here, so it's increasing the derivative. So we say that f prime of x is greater than 0, concave up. And important thing to realize is that again, f prime is increasing, but also that the graph, the tangent lines are below. So in this case, the tangent lines are below the actual graph, because again, it's increasing, the derivative is increasing, which is why the tangent lines are below. Versus for concave down, the tangent lines are actually above, because the derivative is decreasing. So example, concave down, So here, our tangent line is above, and it decreases as we go forward in both situations, and f prime of x is less than 0. Okay? Next, and then we have a concavity test, which is basically just us saying since greater than 0, it's concave up, or since it's less than 0, it's concave down. Next, we have points of inflection. A point of inflection is where the concavity changes. So it goes from concave up to concave down. And the way we identify these is pretty similar to how we identify critical numbers in the number line. The idea is we're going to find where f double prime of x is equal to 0 or undefined. And then we're going to make another number line, call it f prime double prime of x. And we're going to label all these points. These aren't really called critical numbers, but we'll call them for right now critical numbers. And then we just figure out, okay, positive, negative, positive. And it's point of inflection if the sign changes. So the sign changes is point of inflection, which makes sense, right? Because let's imagine this one, right? Positive and negative would be something like this, concave up to concave down. There's a point of inflection right here because the concavity is changing, right? You can visually see that's changing here to here. And the way to visually see concavity is imagine water. So if you imagine water, it's concave up if the water goes kind of like inside a bowl, and it's concave down if the water goes kind of on the outside of the bowl. Right? Water would go like this inside the bowl, but in this case, if it's concave down, water would go like that outside of the bowl. That's how I think about concavity, but that's just me. And there's only a point of inflection if it equals 0, undefined, and if the sign changes, right? Just because it's 0 undefined does not mean that it's a point of inflection. And the counterexample would be this, right? So we have a point of inflection here, or so not point of inflection, it's not. We have the f prime of c is equal to 0 here, but it's not a point of inflection because it's concave up here and it's concave up here, and the point of inflection is not here because the concavity doesn't change. This leads us then to the second derivative test, and this one states that if f prime of c is equal to 0 or undefined, and f double prime of c is greater than 0, then it's a maximum. If f prime double prime of c is less than 0, it's a minimum. So if it's concave up, it's a maximum. Concave down, it's a minimum, which makes sense, right? Functions concave up would look like this. That's a minimum. A function, I got it slipped. It's a minimum. If f double prime of c is greater than 0, it's a minimum, and if f double prime of c is less than 0, it's a maximum. Because again, concave up, like so, means it's a minimum, and then concave down, like so, means it's a maximum. And then if f prime double prime of c is equal to 0 or undefined, this test is inconclusive, and we have to go back to the first derivative test. We're not able to make any assumptions or any statements. If it's 0 or undefined, we have to go back to the first derivative test. And basically the chain of how we figure out extrema, there's really 3 options, right? Closed interval and then 2 derivative tests. So finding extrema, right? If it's a closed interval and we're looking for absolute, we can use a closed interval test. But if it's an open interval and we're looking for relative extrema, we're going to use either the first or second derivative test. Second derivative test is usually easier. That is, of course, you can take the second derivative. If it's not easier, then use the first derivative. But then if the second derivative fails, you have to do the first derivative. So I'd say usually try to do the second derivative test because I think it's easier in a lot of cases. But if it fails, or if it seems really hard to take the derivative, do the first derivative test. Right, you have options. And the commonality is in all of them. You need to find critical numbers, which is an important skill for this unit. And finally, let's do optimization. So optimization, the idea is we're given kind of like a word problem, and we want to figure out how do we get the maximum value or the minimum value in this situation. So the key steps, we want to first identify our variables. Then we want to write our equations. Then we want to combine them all into a primary equation with only one variable. Then we want to find the max/minimum, depending on what the problem is asking us. And finally, using our domain and using the max/minimum we found, we can find our optimized value. So quick run through, let's do an example. Let's say we have a function like so. F prime of x is equal to 9 minus x squared, where x is, or f prime of x is greater than 0. And let's say that the inside this function is a equilateral triangle, like so, right, with points at 0, 0, x, f of x, and then negative x, f of x, right, equilateral, or sorry, not equilateral, isosceles triangle. And we want to find the value of x, or we want to find the greatest area for this triangle. So the first step is we want to first identify what is our equation. So we know the equation is, for a triangle, the area is base height divided by 2. So for this case, the base is going to be from here to here. It can be anywhere, but we'll call from here to here is easy. So the base is going to be from negative x to x, so 2x. And our height is going to be from here to here, which is f of x. So 2x times f of x divided by 2, which is equal to x times f of x. Right, so we have two variables, we have x and f of x. So let's get into one variable using this equation. So a is equal to x times this equation, so 9x minus x cubed. And now we've got a primary equation with only one variable, right? Well, technically we have a, but that's going to go away when we take the derivative. So we take the derivative to find the maximum. So dA of dx is equal to 9 minus 3x squared. And we want to find the maximum or minimum. So let's see, where's the critical number? So 0 is equal to 9 minus 3x squared, right? It's never undefined. It's a polynomial. So 3x squared is equal to 9. Therefore, x is equal to plus or minus root 3. Okay? And so let's consider our domain. X here has to be a number from 0 to 3. Right? So 0 is less than x or equal to 3. And so that means that our value that we're looking for really is not minus 3. It's x is equal to positive square root of 3. Okay? So that's the value at which our area is maximized. So now to find the area, all we have to do is plug it into our formula. So we know that the area is base times height divided by 2. So 2 root 3 times f of root 3 divided by 2. 2's cancel out. F of root 3 is going to be 9 minus 3, which is 6. And we get 6 root 3 as our optimized maximal area. So as you can see, this kind of unit is really useful because it helps us do problems like this. It helps us optimize stuff and figure out max/min values of word problems or functions like we did before. And yeah, that's everything you need to know for Unit 5 of AP Calculus AB and BC. Thank you all for watching, and I'll see you guys all tomorrow. Bye.